Hello, everybody. Welcome. Thank you for joining us today for the Streamin Day of STEAMin from the Arizona STEM and Libraries Working Group. We've got a couple of really great sessions today. We've got 3 different libraries who are here to share some really great STEM activities with you. So we're going to go ahead and kick it off with Linda from the Asante Library.
Okay, hi everybody. I am Linda Shanks from the Asante Library in Surprise, Arizona. We are going to be doing a Da Vinci bridge today. So a Da Vinci bridge is something that Leonardo da Vinci designed in 1502 for a sultan because he wanted a large bridge to go over a span. It would have been the largest bridge in the world, but the sultan didn't like his design because da Vinci was always ahead of his time. So the design didn't actually get built and tested until modern times, but it worked. So let's see. This is what you're going to need. You're going to need 12 pencils and 36 rubber bands, which you should have in your kit. Now, to give you an example of what these look like, this is how big they can get. Ours isn't going to be nearly that big because we're working with pencils instead of 2x4s, but they can be very large. And if you've got the right kind of junctions, they can be pretty sturdy. So Da Vinci had the right idea, and we will skip questions for right now. And we will go to live. Do I need to screen share to get me up there?
Nope, you're on there.
Okay. All right, so you've got pencils like this, and you're going to want to make sure that they are equal. So the best way to do that is pick your 3 spots, end, middle, and there. And with ours, we've really got our website on there. So if you aim for that website on the pencil, you'll be hitting the middle. And to get these on there, you basically just go around 8 times. I'm only going to do this once instead of 36. Okay, instead of 36. So you just kind of get the basic idea. Now, the best way to make sure that you've got them even is hold up the pencils. And if they're lining up, you're right on the money. Now there's 2 different kinds. You can do just the ones that are going to be on the edges with 3, and then 2 for the ones that we're going to weave. But if you're trying to build one of these by yourself and keep it balanced, you don't want to be paying attention to which pencil you're picking up. You want them all to work. So let's do a shot down, and I will show you what one looks like when it is finished. It looks pretty rickety, especially when I move it around, but the design of this bridge is that it is stronger the more tension it's under. So they're pretty amazing. So I wanted to start with the test because I thought that would be easier. Now, put tension, and you can do quite a bit to this, and it won't move. Take the tension off, and it doesn't work out so well. So that is the basic structure. Now, I'm going to take the camera down again so that you can see how it's done. Let's see if we can get a good shot. Basically, it follows a pattern. You've got, let's see if I can get it on the edge. You've got down, and then top, top, top. Make sure you're lining this one up with the middle. And now we're going to weave. In order to weave, we've got to lift. This is the trickiest part. And actually, it's a little easier because I can watch the camera. Oop. I can watch the camera and see the other side. I started working on this, practicing about a week ago, and it took me about 3 days to get to the point where I could do it consistently. Weave, weave, and when you come down, make sure you're getting those rubber bands in that joint, and it's wobbly, but it will be wobbly. Now, so we had top, 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 weave. Now we're going to go to the other side, put this one down, lift, whoa, weave, weave, and carefully down. And then you can kind of like tighten up, make sure that it's going to stay stable. And we're going to do that again. Now, theoretically, you can keep going, but it's going to get longer and shallower. So it depends on what you want to do with your pencils. So down, lift, weave, weave. And that is your Da Vinci bridge. So the longest part of this is putting on your rubber bands. And it's best to start with them even, the way I demonstrated with them lining up. But when you get to this point, you can always adjust. If you decide that you want it a little wider, a little more stable, or a little skinnier, you can do that by moving your rubber bands. Okay, so you can do this by yourself, but if you do it by yourself, it's going to require some patience. If you do it with two people, you need to make sure that you're coordinating, because if one person knocks one direction and the other person is going the other direction, it can fall apart pretty quick. So are there any questions about our Da Vinci bridge? Oh, so something else, we gave you a video in our kit so that you can link to it with a woman who can do it in 60 seconds. I don't think I managed this in 60 seconds, but she can do it amazingly fast. And if you look online, you can also find other things that are called tensegrity. And they have like different things that basically it's tension building, where it looks really, really fragile, but it's incredibly strong. Let's see, some of the STEM careers with bridges. Okay, the biggest one would be mechanical engineering or civil engineering. So those are the people that have studied the physics and the mechanics that can make different kind of bridges that will span the San Francisco Bay, you know, the one that everybody knows about, the Brooklyn Bridge, which was one of the earlier ones. That's something else. Let me scroll back down for just a second. So you see that this is the dome, or I should say the half dome. And this is naturally one of the strongest shapes in nature. So it makes sense that the Da Vinci Bridge and a lot of other design bridges would follow that. Okay, let's see. How big? There is an example of a Da Vinci bridge with a slightly different design. It's a little bit more complicated, and it is in Norway, and it is huge. And that's one of those things that you can look up and see. And of course, our Da Vinci bridge has like large gaps, but when you make one that's more permanent, they have the planks that go across. It adds stability and it makes it easier to travel across. The nice thing about this design is this is something that you could do, and with a 2x4, you could do it and you could move it. So it's a portable bridge. Okay, anything else? Yes, this arch shape. It took me a while to think of arch. This arch shape is used in a lot of construction. It's not only used in bridges, but if you've ever seen pictures of the Roman aqueduct, a lot of Roman things, especially the aqueducts, were built with these arch shapes. And in the case of the aqueduct, they repeated down the line. So you had multiple arches giving support to this heavy water that was traveling for miles. And the Colosseum, that was also, you know, they had arches in the Colosseum. So it's a really strong shape. If you're doing it with stones, you build up from the sides, and then you have to have a keystone which holds it all in place. But once you get those things kind of like this, once you get that balance, that physics and that tension right, it's ridiculously strong. Oh, at Asante Library, we have right now, because we're easing back into programming, we have 2 STEM programs a month. The first Monday of the month, we have Maker Fun, which is for school age kids. And then the second Monday of the month, we have Teen STEAM, which is for tweens and teens. And so every month we do a different activity, and it's hands-on. Everything you need will be here. And a lot of the times we have different crafty Maker Fun kits that are take and makes. So come in and see what we've got. And as we ramp up to like full programming schedule, we'll get back to where we have pretty close to 1 area of Maker Fun every week with different ages.
Awesome. Thank you so much for that great presentation. I see we've got another question. Do you have any other fun STEAM books to recommend?
Yes, and the nice thing is, if you go to mcldaz.org, you can look online and see what we've got before you come into the library. Because we have some stuff here at Asante, but Maricopa County has 18 branches. So it's nice to go and see what we have all over the county. And then if there's one thing that maybe we don't have that Northwest has, or Southeast or Gilbert, any of those areas, if there's something they have, you can place it on hold and our courier system will bring it here for you to pick up if we are your home library. And it's always fun to come in and look around, and make sure when you come into a library, if you have anything specific you're looking for, ask your librarian, because usually things are in one specific location, but sometimes we will know the stuff that's in a different area that might be really cool for what you're looking for. Let's see, recommending, probably the best STEAM book that I know is, there's one, it's 100 Maker Crafts. That's probably my number one. My second one is, there's one that's really good on cardboard engineering. And one of the things that I would, well, I probably shouldn't say this because I haven't brought it up to my boss yet, but one of the things that I would like to do is get a cardboard club going. So cardboard has all kinds of engineering, but you make really, really fun stuff that you can use.
Yeah, thank you so much for the awesome presentation. If there are any other questions, please feel free to keep sending them in the chat. But I think that will wrap up our first session here today of the Streamin Day of STEAMin. And so we will be back in just a little bit to go on to our next activity from the Auction Indian Community Library. We're going to be working on some awesome LED circuits. So thank you so much, Linda, for your quick demo here. And we'll see you all in just a little bit. Hello, welcome back, everybody, and thank you for joining us here for session 2 of the Arizona STEM and Library's Streamin Day of STEAMin. We are going to go over to Matthew Cross from the Auction Indian Community Library, who's going to be doing a really cool paper circuits activity.
Okay, so we will be working on an anglerfish paper circuit. I like this one because, well, I like paper circuits to begin with. They're very fun. They're very colorful frequently. And I like playing with the LEDs. I like making things glow. Much like the lure of an anglerfish. And that's where this one came up. So for this, as I was saying previously, you'll need the contents of that packet, which contain 1 anglerfish card, 1 set of instructions, which I will not show, and a package of parts. So parts contain, once you tear off the seal, because they are small, and you won't believe how many times I've lost parts on these. They go everywhere. One CR2032 battery or coin cell battery, one LED. Your LED may be white, red, blue, or yellow. I think I have clear, and a length of copper tape. What you will also need, but is not included, is something to cut with. A pair of scissors is the usual option for that. I often use a cutting blade for, well, specific name brands excluded because I can get more precise, especially with the teeth. Those teeth are very hard to cut out. And something to color with. I tend to use color pencils because I like to shade things. You, of course, may use whatever you have on hand: crayons, markers, permanent markers, watercolors, finger paints, because finger paints are awesome, and oil pastels if you're feeling very adventurous. I don't like using those because I tend to make a mess with them. And I have ruined too many articles of clothing that my wife won't let me use them again. I mean, that's just the way that one is. So you can color your anglerfish however you would like, because it is your anglerfish. I'm certain you can go online and find all sorts of pictures of all sorts of types of species of anglerfish, because there's not just one species, there are many. And while I'm coloring the fins, I have a question for y'all. That's my Kentucky coming out. Does anybody know why an anglerfish's lure glows? Anybody at all? Because when I found this out, I was super surprised. I did not see this one coming. Any guesses? Anybody at all? Like the jellyfish. Well, bioluminescence, yes. Bioluminescence is correct. They're not born that way. They get it somehow by ingesting the bacteria that bioluminesce. Is bioluminesce a word?
Sure.
Okay. I think it's a word. So they ingest the bacteria, the bioluminescence, and it goes into the lure, so it glows. And it varies over their age, apparently. I thought that was really cool. So once you have, yes, all you need to do to glow in the dark is swallow fancy bacteria and grow one of those somewhere, maybe at the end of a finger. Once you have colored in your anglerfish, and I did mine very quick because I'm watching a clock and I want to make sure I have time for questions. I don't want to make sure I don't mess it up. That's why I'm also using the scissors, because they are faster. And I'll start from a different end. Once you have colored in your fish, you need to make sure you do two things when you cut it out. First, don't cut that off. I've done that a couple of times. That means your anglerfish is not an anglerfish, it's just a fish. And the other is to not cut that off. That will be our battery flap and where we will place our batteries. Because you can't make a paper circuit without a battery. Well, okay. I guess I'm technically wrong on that one. You can totally make a paper circuit without a battery. I mean, it won't glow. But as I'm fond of telling the kids when they come into programs, especially when they're doing the art stuff, you do you. If you wanted to make it purple and not glow, it's your creation. If you want to make it, if you want to add more stuff to it, if you want to add a fourth fin somewhere, or an extra row of teeth, that's your creation. You can do it how you want. But as you know, I want mine to be an actual paper circuit, so I'm cutting out the battery flap. And then, once I do that, I can be super fast with the rest. Oh. Well, I can at least try to be super fast. Like I said, I normally use a cutting blade instead of a pair of scissors. I'm going to leave my fish like that because we're working on up here now. And don't forget, when you're done with your extra paper, put it in your recycling bin. So we will now need the LED and the length of copper tape. We want the copper tape to run down from the lure along the fishing rod and back up to the battery flap and over to the other side. We want to do that one first. There will be another length of copper tape that we'll need for the other side. And this is one of those, I'm just kind of running it down and getting a just about measurement because well, you might not have a ruler handy. And I frequently don't have one when I'm doing this. Now the copper tape is sticky on one side and not on the other because, well, it's tape. Arr, ah. And we want it to go on the top like that. And down the fishing rod. And I like to do the fold to make that one kind of super sharp. And realize I somehow, through my overexcitedness, stuck the tape to itself. But that's not too much of a problem. You just have to be careful when you fold it over. And I made that a little bit too long, so I'll stop there. We want to fold over. I'm going to fold our battery flap over because we'll have the battery around here. All right. We got one side. Now, for the other side. We'll do our very rough measurements again. And you should have a significant, I hope, if I measured correctly when I was putting these together, a significant amount of copper tape remaining. You will need some of that for the next step. I'm going to try and do this in such a way where I don't stick the copper tape to itself. There and down the road. And over like so. Yours doesn't have to be the same length as long as when you fold them over, the two pieces of copper tape touch. We will be placing the battery in there to complete our circuit once we attach the LED. So now our next step is attaching the LED. I like to do it this particular way because it makes the fish more three-dimensional, but you can do it others. Conceivably, you could bend the legs and push one through and tape them down that way, but I like to lift up the lure and put one leg on one side of the paper and the other leg on the other. In such a way that they're both touching the copper tape. This is where we also will use our extra bit of copper tape. This copper tape is conductive on both sides. So it is both conductive on the shiny copper side and the more matte. Sorry, there's a dad joke there. Sticky side. Now, some of you may be asking, Mr. Mac, I noticed that the legs of the LED are two different lengths. Does that matter here? Well, yes and no. For several paper circuits it does, but for this particular one, it doesn't. You can have the long LED leg on one side, on either their front or the back, and of course the short would be on the other. All that matters for this one is that, you see that? There we go. Is that the leg is on the copper tape and that there's another piece of copper tape making sure it sticks well to it. Ooh, here's time for another question. Does anybody know why the legs of an LED are two different lengths? I shall pause here while you Google an answer. Yes, that is correct. One side, the long leg is the positive and the short leg is the negative. So if you remembered which was your long leg and which was your short leg, when you stick it down, you'll have a better chance of getting this circuit correct the first time. Now that we placed our LED on the copper tape, we've taped it down well with another piece of copper tape. So there's a good connection. In fact, I'm going to press down even more because that connection seems to be the place where it fails the most time for me. we'll now get our battery. Our battery is like other batteries. There is a, like, you know, the double A's and the triple A's and the C's and D's and all the other sizes. There's a positive side and a negative side of your coin cell battery. The side with the writing and with a plus on it is the positive side. The bumpy side is the negative side. We want the positive side where the long leg is and the negative side where the short leg is. Now, if you don't remember which one was which after you taped it down, that is no big deal. As this is a paper circuit and we're using a battery flap, we can easily change which side of the battery we have on. Now, I'm going to start off with positive side up. And we can see that I guessed wrong. I'll set it down. Oh, I saw it flash. And I guessed, well, by the process of elimination, I was correct. And I just realized you can't actually see the fish from this side. Let's fix it. Wow, I totally lost my battery too. My other one stayed on. So if you happen to have a paperclip handy or an extra piece of tape, should have added that in the things you need that are not included in the packet. We have an anglerfish with a glowing lure. And of course, yours is, you know, probably colored a lot better. And most likely also completely cut out. But it's a demonstration model. Yes, I agree. It is time for some seafood. There's a sushi place in town that I might be going to later today. All right. And that's all for this paper circuit. Does anybody have any questions while we still have a few minutes? The question is, what else can you make with paper circuits? Well, quite frankly, artwork is like paper. Well, okay. Anything you create, any picture you can draw that you would normally, not normally, but that you would draw like a lamp or the sun or want shadows in, seems perfect for a paper circuit. And there are many ways you can do it. Usually some copper tape, an LED, and a CR2032 battery. They're perfect for it. I specifically say that type of battery because you can find those everywhere. They seem to be the standard. What are you going to name your anglerfish? Well, I tend to name most of my fish Frank. My daughter named her/our fish Moonlight. I think that may be more appropriate for one, as it does glow. Ooh, Chuck. Chuck's a good name too. What type of STEM jobs work with circuits? Okay, anything, any electrical engineering, computer science. Those are ones you're definitely going to work with circuits. I can't remember where we had one earlier. There was a wonderful meeting we had a couple months ago in which they described how they were bringing in apprentices to learn how to make the wiring harnesses for helicopters in the valley. And I can't remember where, and I'm certain somebody will probably pipe in with that information while I'm babbling along. That circuits, anything that has electronics is going to have a circuit in it. It's going to need power to run from point A to point B, so you're going to have to learn how to wire it. Yes, that sounds about right. What STEM resources are here at the library? Well, we have lots of STEM resources. We have a wonderful makerspace in which I am in right now, in which you can learn how to do all sorts of crazy things. You check your local library, they may have one as well. For example, here we work with Raspberry Pis and Arduinos and robots of all sorts and sizes. We do coding programs in multiple languages, and we like also to make practical projects too. And when I say practical, I mean fun. We're currently working on making video games. So if you have a code club at your local library, I suggest you go and ask about making video games because, well, everybody likes to play video games.
Awesome. Thank you so much for the great demo, Matt. That was really cool. I'm super excited to keep playing around with these paper circuits and see what else we can make. I'm going to take a quick pause and then we will jump over to Miss Jenny from the Peoria Public Library, where we're going to be working on soda straw and balloon rockets.
Ooh.
Welcome, everybody. Thank you for coming back to our third and final session of the Arizona STEAMin Library Streamin Day of STEAMin. And here we are with Jenny from the Peoria Public Library, who's going to show us a really awesome activity with soda straw and balloon rockets. Thanks, Jenny.
Thank you, Claire. Yes, so I'm here at Peoria Library. I'm at the Sunrise Mountain Branch that's all the way up at 99th Avenue and Lake Pleasant Parkway. So if you're in the West Valley, come and say hi. And you may have noticed that even though I'm in a library, it looks like I'm in space. And that's because I'm all about space science today. The fancy term for space science is aeronautics. If you've ever heard of NASA, that's actually what it stands for, is the National Aeronautics Space Administration. That's what it actually stands for. And in fact, the experiments we're doing today is from the NASA at Your Library website. That's where I got all my fun stuff for you guys. For this experiment, hopefully you were able to get a take and make kit from the library. If not, don't worry, because these are all things you can do with items you find around your house, such as you are going to need a soda straw. If possible, you can even find 2 soda straws. For this experiment to work, they do need to be of 2 different sizes. So like the bendy straw, you need a really skinny one, and then you need a fatter one. Fatter ones you can normally find at any fast food restaurant you go to, everywhere from Wendy's, Culver's, you name it, they're gonna have the fatter ones because they're gonna be able to fit over the tiny one. Now, if you don't have a fat straw, that's okay, because you can also use paper. So in fact, if you got your kit, I want you to take out the fun little template we have for making your own soda straw rocket. You're also going to need from around your house that wasn't in your kit, because I know everyone has tape and scissors. You can use masking tape, you can use scotch tape, just any kind of tape. You will need to grab that real quick, along with your scissors. And then of course, when we go to our second set with the balloon rocket, you will need a balloon and some string, but we'll get to that in a minute. Right now, we're going to focus on the straw rocket, which is needing straws. So like I said, you can either use a regular fat straw, and you can take some tape, and you're going to want to cover over one side of that straw, because if you blow through a straw, your air is going to go right through. But this way, by putting tape on one end, you're going to trap the air and be able to transform it into a rocket. Now, like I said, if you don't have a thick straw and you only can find one straw, or you don't have 2 different size straws, what you can do is you can take a strip of paper. So if you have your template, take out your fancy scissors. Some of you got pre-cut ones, some of you didn't. Just get what you get, you don't throw it. And you're going to need a nice long rectangle. So even if you don't have the template, it's basically what's going to look like. It's a nice long rectangle. And then what you're going to do is you're actually going to need a pencil. And you're going to wrap your rectangle around your pencil to basically make your own straw of sorts. All right. So it's going to roll around. And then you're going to take your tape and you're going to tape it together. And because you're making it, what you can do is you can actually create a cone, like a nose cone, like a real rocket, and kind of tip it at the top, roll it around, and make a rocket tip. And that's where we get to be like scientists, see, because you can actually experiment where you can choose, you know, maybe the first time you have a certain length and you don't like how far it goes. Well, you can go back and make it again, and maybe you make the nose longer. Does that make it go farther? Does that make it go shorter? Maybe you make the nose shorter, and maybe that changes how you do it. Because if you notice, inside your kits, if you bought one, I even gave you this really fancy looking graph that says straw rocket data analysis. And then there was one that was a straw rocket data log. The reason that is to kind of further your scientist thinking. And you can be like, okay, trial one, it was about 1 inch long and it went, you know, 2 inches far or however far it went. And then maybe the next time you're like, I made a nose cone rocket that was 2 inches long. And oh, what do you know? It went 5 inches. And so that kind of gives you a sense of where your data is. And you can even if you really are into math, I know some of you are into math. I may not be so much. I like the science side more than the math side. But if you like the math, you can actually graph it and see the different points of how long or how short makes a difference in how far your rocket actually goes. Okay, so those are the kind of fun science extensions. Okay, so now I've got my paper, and I'm going to really make sure I tape it because again, I don't want the air to go anywhere but to the top. See, on Earth we have gravity, obviously. So birds, they go against gravity by flapping their wings. Well, for a rocket, it uses what's called thrust. And it's going to use that thrust. It's going to take that energy and momentum and thrust it up away from Earth's gravity. So that's why when you're making your self-made one, you want to make sure no air goes anywhere because you want to get good thrust. Otherwise, the air is going to leak out and your rocket's not going to go anywhere. All right, so now that I've got my rocket nice, and of course yours is going to look a whole lot prettier than mine will, but it's the idea. Just like Matt's little anglerfish that he did. Okay, so this is where we get to the fun part. So we're going to first take our, oh, I almost forgot. So we can also do it just like that. But that doesn't really look like a rocket. You can also add fins to it. So again, if you got your template, that's what these crazy looking guys are. Those are fins. So we're gonna cut them out. If you don't have it at home, if like you don't have the thing, you could just take more rectangle strips. See this one? This one is just good old-fashioned rectangle strips because this is kind of the shape we're going for. It's basically like a Star Wars X-Wing, okay? So you can do it that way. But if you've got your fancy little nose fins, they look a little bit more like a traditional rocket fin does. And again, that helps with our aerodynamics that we're doing with our aeronautics space science. And I'm cutting it out. Hello to everyone, by the way, anyone who joined the chat a little bit later. Oh yes, aerodynamics, I did forget to, that is a fancy word that means the way air moves. So, and that's why it relates to aeronautics. The aero, A-E-R-O, is basically the fancy term for air. Why it sounds so similar. Okay, I've got my fins all cut out. So now I'm going to take my tape, I told you we're going to need it, and I'm going to tape them to my rocket. So what you're gonna wanna do, obviously you wanna tape it to it, but once it's on, you're gonna actually bend it boop, at a 90-degree angle, boop, and you're gonna do that again. Again, even with these fancy looking ones, you're gonna wanna have that X shape because that's gonna give you the most aerodynamic shape. It's gonna help the air pass through it the best and give it the thrust it needs to actually break free from our gravity. That. You might need to use more tape. Again, we're thinking like scientists. Every experiment is a little bit different. So yours may look prettier, yours may look different. And that's the beautiful thing about scientists. It isn't always about getting the right answer the first time. It's about trying again, again, and again until we get the right answer. All right. So now I've got, looks a little cray-cray, but it kind of looks like a rocket now. Yeah. So I'm going to take my straw. I kind of like the bendy straws because then I can bend it and it really looks like a launch pad. All right, so we're going to do some blast off, see how far it goes. All right, I'm going to count down 5, 4, 3, 2, 1, blast off. And that is my soda straw rocket. And then let's see, I'm actually going to take it off of here. I'm going to try it on the actual straw because it is called soda straw rocket. So let's see if it makes a difference between my homemade little paper rocket versus an actual soda straw. This is a QT straw, which is like really, really big. Oh no, I'm losing tails. No losing tails. All right. Come on. You gotta stick with me. You gotta be able to make it to the other side because we gotta make it into space. All right. And again, count down. Oh, make sure I've got my nice 90-degree angles on both my fins. There we go. Now I've got a nice X. All right. 3, 2, 1. Oh my goodness, look at how much farther that one went. It's longer. So see what awesome ways you can think like scientists and experiment. So that's the fun soda straw rocket. Now, the balloon rocket is very similar. You're still trying to use thrust to get you away from the Earth's gravity. But in our soda straw one, you notice you're using your very own air, which, I mean, even the person with the best breath support's only going to get so far. A balloon has a lot more air and a lot more pressure that it can build up, all right? So for this part, you're going to need a balloon. You're going to need a straw again, and you're going to need string. Now, I say string, but it really should be more like fishing line or something. You basically don't want friction. Friction is when things rub together, and what will happen if like you use actual yarn, it'll slow it down and drag it down. You don't want that. You want it to smoothly glide along it. All right. So that's why the ones I put in kits, it's kind of like this plasticky kind. Remember the ones you make bracelets with and stuff like that? That's what I use. You can also use fishing line. It just basically needs some sort of string that doesn't have cloth or fiber. Okay. And you're going to take your tape and you're going to tape it to, you can do a chair, you can do a table. Maybe if you have a friend or a family member, they can hold the other side, but you basically want this side to stay stationary. So I'm going to tape it to my stars because I'm going to blast off into space because that's, of course, what we're doing. We've, of course, been to the moon with NASA and they're trying their hardest to get to Mars. About 2024, they're hoping to launch something that will actually get them to Mars. So, you know, and then they'll take about 6 months to get there. Oh, gotta grab mine. Threw away my straw. I'm gonna need. Well, I didn't throw it away. I ricocheted my rocket. Okay, because I'm actually gonna need it. You can use the bendy straw, but then you have to cut off the bendy part, and it's also skinnier. And I want to give myself as much room as possible, so I'm actually going to reuse, recycle my lovely straw, and we're gonna thread it through my lovely string. The downside of not having friction, it's just an every way for me to keep a hold of it. Oh, perfect. So that's that. Now this is where it gets tricky. We're gonna blow up our balloon, but we don't want to tie it. All right. So, and then once it's blown up, we're gonna have to try and very carefully attach it to our string. Because you can try and do it before it's blown up, but as it blows up, then it'll come off, and that's gonna be awkward. So I can at least do a little bit of prep and put that there. Okay. Then I'm gonna actually have to blow this up. And hold it, all right? And I learned the hard way when I was doing this experiment myself. It does matter which way you face your balloon, because again, we're doing thrust. So whichever way you want your rocket to move, you actually want to face your balloon in the opposite direction. So you got to think a little backwards. It's one of those, you got to go left to go right kind of thing, because we're going to want to do some thrust. It's really interesting. You only have two hands. If you have a friend, you need help. Okay. So here's my lovely balloon. Got my lovely balloon rocket. So let's see if I can get this to work, okay? So we're gonna go. I lost my string. See, this is how real science is, kids. It doesn't always work the way we want it to the first time, but try again and again and again. That's true science. It's about finding the answer. It's not about knowing the answer, right? That's the difference. Okay, so let's try this out. 3, 2, 1, blast off! I lost my string. See what I mean? But you get the idea of how a balloon rocket is supposed to go. It thrusts it away from wherever you're standing because the air is escaping from this end and pushing, thrusting it forward away from our Earth's gravity and creating the rocket. So that is the aerodynamics of aeronautics of NASA and space exploration. So those are kind of fun ways at home that you can see. These are called models, and those are ways that scientists actually use models so that they can figure out before they do the real thing how it's going to work. All right. So does anyone have any questions? You want me to try the balloon one again? See if it works the second time. Oh, okay. I'm doing pretty good on time.
No questions so far. Do you want to do it again?
Yeah.
Let's do it again.
All right. Probably gonna, well, let's see if I can blow it up while it's still attached. All right, and what I'm gonna do is I'm officially gonna make this thing smaller because I think that'll help me have a better journey by having a smaller straw. And then I'm going to really take this thing down because I want it to go into space. I don't want it to go on the ground because that is the opposite of what we want rockets to do. That actually has happened in NASA in the past, and it's never worked out well. We want cars on the ground. We want rockets in space. All right. So that's that one there. Oh, hello. Got no strings. Down. All right. Just need for you. All right. Let's see if I can get this to stay in space this time around. Right. 3, 2, 1. Blast off. Yay! And that is a successful mission. All right. So, oh yeah, so thrust is what birds use in small constant motions when they're flapping. And the thrust is obviously for a real rocket. We're of course using balloons and our own air. They use fuel. They take like gasoline and they burn it ridiculously hot temperatures. And then it rounds it up and it makes like a tiny explosion at the bottom that then forces it finally to thrust it away. That's why it takes a long time. If you've ever watched a launch, it takes like, they count down, and even then it's like slowly, slowly, slowly. If ever you watch it on TV, or you can actually go on YouTube and watch the nice ones from the 1960s, and it takes a good long while for that rocket to go up high. I mean, even when you're flying in the plane, it takes a long time to just take off from the ground. So yeah, that's the beautiful part of our gravity, is it keeps us down. But when we want to get away from it, oh, we got to get creative. Okay. Let's do.
And Claire said, never thought about how slow it starts off.
Yeah. True, true. So let's do.
She also has another question.
Oh,
Sorry.
oh.
What STEM resources are available for families at Peoria Public Library?
So I try and do, right now we're doing it more like a take and make, just because we were transitioning from, at Maine, we were in the midst of a remodel for about 7 months. So we didn't have any space to actually do in person. So I've been doing take and makes, where you actually, once a month, there's like little kits that people can grab from either the Sunrise Mountain, where I'm at today, or the main branch, which is down at 85th Avenue in Monroe near Grand Avenue. So those are the 2 locations, and they can pick up kits. And then about a week or so later, I put a video on, just kind of like this one, that shows you how to do the science experiment with the materials in the kit. And again, I try and make them mostly materials you can find around your house. That way, if, you know, because I can only make 50 kits, you know, I'm not made out of kits. So, you know, like this month, I was trying to tie it in with, we had a butterfly program where we had monarch butterflies journey over at our story walk. So we made tie-dye, coffee filter butterflies. So that was, that's kind of what we're trying to do. So every month I try and have something. I don't know what I'm going to do for the summer, because it's all about oceans of possibilities. So I'll probably do something with oceanography, but I don't know what yet. But I am hoping for next month, Earth Day is coming up, and we're going to be all about bees, the buzz about bees. So I'm definitely going to be doing, it's called a bee buzzer, and it's a way to make the sound of a bee with items you find around the house. That's the thing I hope to do in April. And then in May, I'm probably going to do space themed again, because we're having West Valley Astronomy Club come out and do stargazing. So I want to have my science tie in with that. So we're going to do lunar, I just blanked on the word, but the moon phases. There we go, lunar phases with Oreo cookies. So that one's going to be hard to convince kids not to eat it before we do the experiment. So, but those are the resources we try and have available. And of course, we have all our science. We have a lot of picture books that actually are STEM related, that have science, you know, things that float, things that don't. Marsha's magnetic, CC Love Science. You know, we've got a lot of picture books that have kind of stories that sort of encourage that thinking, as well as actual nonfiction books that are about science experiments and all that kind of stuff. So, that's why I brought my Cookie Beaches from City of Peoria water bottle, so I can keep hydrated. Let's do, I want to see. I can make my, I was very sad by my paperwork. I want to definitely do my straw rocket beta log, and I want to see if I can make it go farther, because that was sad. I blew it and it went up and straight down, which is not, I mean, it's okay. That's not really what a rocket's supposed to do. So I'm going to try this again. Taking my scientist, doing it again. That's actually the engineering technique, is think, test, evaluate, and repeat. Over and over and over again. You think of an idea, you test it out, see how it works, you evaluate what you can do to make it better, and then you do it again until it comes out the way you actually had it in your head. Because we always have great ideas in our head. It's getting it out in the real world that's the hardest part. All right, so lovely little tape going, a nice 90-degree X-ray angle. So I'm going to try it more angled because I did it like this before, and that's why I went up and down. So for trial number 2, I'm going to angle it and see if I can get it to go further, because now even though the thrust, it has less of resistance. But going straight up, guess what things are going to do? Because we live on Earth and we have gravity. It's going to go straight down. So if I angle it, maybe I can get it to catch the wind and go that way. So see what trial number 2 gets me. 3, 2, 1. Last off. Hey, that was much better because I angled it. See what I mean? How science can help you think through things? So fun. All right, so let's see. Nice draw, rock, dialogue. The length of the nose cone didn't change, but for trial 2, I did do a different distance. Oh, that's interesting. They give you different trials with the same length. So you can even see, like so, I didn't actually change anything about the body. I just changed the angle. And that's another thing about science is we have what are called controls and variables. Control means one thing stays the same all the time. So that way you change the variables. Everything else will change. So that way you see what the difference is, like that. Everything stayed the same, control, except for the angle. That was my one variable. So, grab it. Sorry for that frame there. But yes, that is National Aeronautics Space Administration, or NASA, at your library experiments. There's a balloon rocket, soda straw rockets that you can do at home. I've even seen one with a 2-liter bottle and PVC pipe. You make a pump and you blow it up, but I didn't have that much PVC pipe, so I didn't do it. But those are not, that's another home rocket that you can try, all about thrusting things away into space. So I made such a mess over here, but that's also what sciences look like, is that we get a little bit messy to be able to get to our final product. Oh. I didn't want to do an experiment that was too long or too short, so I was trying to go for the middle. So also make sure if anyone actually had questions, that I would have time to answer them. And lovely Miss Kathy from Sunrise Mountain is my camera and laptop assistant, so that way I can be here shooting off rockets. And that's also how NASA works too. The cool astronauts that everyone knows about are the ones who actually get to go in space. But then there's a whole team of people you never know about who sit at the computers back in mission control, making sure that those astronauts get into space. You've ever seen Apollo 13? There were 3 men on the actual ship and dozens of men in the actual mission control trying to figure out how to get those 3 guys back home. So that's how any organization really works. A lot of people behind the scenes helping the people in the front of the scene actually making it work.
Claire loved your analogy.
All right. Well, thank you guys.
Awesome. Thank you so much for the presentation, Jenny. That was really fun. And thank you to everybody who tuned in either on the Zoom or on our Facebook live stream for the STEM in Libraries Streamin Day of STEAMin. Well, thank you so much. If anybody has any questions for any of our speakers today, please feel free to send them to us. And don't forget to check out all of the awesome STEM resources at your local libraries and on the SciTech Institute website.